Hello, hello. Okay, I'm back really quickly because we got a very easy problem that we already did before in CTI in 101, and it is valid anagrams. Back at it again in 301. So, that's what I'm gonna be doing. So, valid anagram is pretty simple. We're given two strings s and t. We want to write a function that determines if t is an anagram of s. And an anagram, simply put, is just the string's characters can be rearranged to make the other string. So nagaram and anagram, you can rearrange this to get to this. You cannot rearrange car or car to get to rat. You can rearrange car to get to rack. I forgot the name. It was. I know. I mean, yeah, you could do that, but yeah. So yeah, that's basically all it is. Pretty simple. The naive approach is to sort the string, so sort the characters in the string, and then compare them one by going through it. The optimal approach is to actually take advantage of a mathematical property, which is not really that complex. It's just the fact that you can reorder sums, basically. So all characters have an ASCII value, and if they have, and an anagram basically just has all of the characters be the same. It's just in a different order, or it could be in the same order. So, yeah. Uh, because of this, you can just count or keep track of the ASCII values of both of them. Actually, wait, would that be more efficient? Let me try it. Rather than doing this, let me try freak 1 is equal to 0, freak 2 is equal to 0, and then we just freak 1, and then we just add that to it. Or I guess this would get pretty high. This would go pretty high because of this. I wonder if that causes integer. I don't know. I mean, Python it probably wouldn't. I feel like in C++ maybe? I'm not sure. Uh, and then we just return not, we negate the difference between them. So freak 1. Oh, I guess we could just do freak 1 equal freak 2. Did that just work? Damn. Ah, that's why. Okay. See, I think I probably did that last time, didn't I? Yep. Same thing. Uh, okay, so I just answered my question about this. Okay, so the reason I chose the approach with the array, I forgot why. I just remembered that I did it and that it worked and it made sense to me. The reason we do that instead of just counting the difference is because counting the difference will give us ASCII values that will be the same regardless. So in the case that we had earlier, or that failed for me, was where we had different characters, but the distance between them was the same. So yeah, or well, it could be the distance between them is the same, or it could be that the ASCII values all added up together to get to the same thing, but they actually had different ones. So like, let's say we had I don't know, let's say we had one that had an ASCII value total of like 10. And then you had a string that started off with 7, then got 1, 1, and 1. And then you had another string where it had, I guess this isn't really a good example. Or I guess it is. 3, 3, 3, and then 1. That would not be the same, but both of them would get the same ASCII value at the end. So the reason we do this list approach is because then you have to worry about each character on their own. You separate them. So this is the O of n space and time solution, where we basically keep track of the frequency of each character in the alphabet, since the constraint says that we only have lowercase English letters. So we're keeping track of the frequencies. At the start, it's all 0, so we have 26 characters that are equal to 0, and we can find the index of them by using the ASCII value minus the ASCII value at the start of the alphabet. So that'll get us the index that we're looking for that represents the character that we're looking at. And then we're just going to increment it by 1 for the first string's character, and then we're going to decrement it by 1 in the second string's character. What this allows us to do is it allows us to basically cancel them out. So if string 2 has all of the same characters as string 1, at the end of all of this, all of them will be canceled out because we will have the same number of decrements as we had the same number of increments in the same characters. So that's why at the end we just return the negation of any of the frequency. Any will return true if it finds any truthy value in the list. A truthy value would be anything that is non-zero. And if we find anything that is not 0, then that means we found a we found something that causes them to be like 2 different strings. So if there's a different character in it, that causes there to be a non-zero element in it, and that causes any to return true. And if any returns true, that means that there is a character that does not match between the two, and that's why we negate it, so then we return false. And the other way around, if we look through it all and find no non-zero, or if we find all 0, if all of them are 0, then we return this will return false, and then we just negate that and we return true. I could have used all, and then I could have done that all of them are 0, but that would go through the entirety of the thing every time, and I'm pretty sure any breaks out early once it finds any truth value. So it'll be a little bit faster, it's a little performance increase. I'm not sure if it's really worth it in this case because I feel like it doesn't help with the readability, but it's fine. It's not something super complex, so it's just negating the any function, and the any function just looks for any non-zero element in frequency. So yeah, that's pretty much valid anagram. It's O of n time O of n space. Well, not O of n space actually. It's O of 1 space. Constant space. The reason it's constant space is because there's only 26 characters in the alphabet. This will never change no matter how long the string gets. If the string was 5 times 10 to the 4, which would be 50,000. So if the string was 50,000 characters long, if both of them were 50,000 characters long, that would not change the number of elements in frequency. That would always just be 26 because it represents 1 for each. Each element represents the frequency of 1 character in the alphabet. It's lowercase. So yeah, that's pretty much it. O of n time O of 1 space, constant space. So linear time, constant space. That's valid anagram.